아, 좋은 지적이에요. 대학원 수업도 이걸 실수를 해갖고 반을 날려먹어서 학생들이 원성이 자자했는데. 네, okay, so so in this case, so this is only dependent on the x, which is coming from the outer for loop. So it can be extracted out of the inner loop. Okay, so in that case, let's see, x, g of an x, and then y, so g was taken out, f x comma y dy, right? So in this case, so this part will become our marginal distribution of x, right? So again, yeah, it's basically the same thing where we consider the nice, smooth, like a mountain-like a function, and then squeezing them out, and then adding all the waters along that line, right? So in that case, let's just try to understand from the perspective of this integration. So from here, so this is like a 4 I equals 1 through n, and then this part is like a 4 j equals 1 through m, for example. Okay, so in this case, so we are fixing x part at the outer loop. So given the fixed x, okay, so we can consider this situation as x being fixed. So x being fixed means from the two-dimensional distribution, x is fixed, right? So along the x direction, we have a certain or particular value of an x, and then that surface on that function, and then we perform the summation or addition using this integral. So we are adding all the values along that line, right? So we perform that operation on every x values, okay? And then that is basically squeezing the two-dimensional functions along the y-axis. So that way, so it will become f of an x, and so altogether, we will have this guy. So integral over x g times f times dx. So that is exactly the definition of expectation of g of an x. Okay, so that way we obtain this, and then the second term will result in the same thing. Questions? Okay, so yeah, it's so trivial. And this, okay, so in this case, yeah, so f, x, and y, two random variables are independent, and then this relationship is true. And then you guys know kind of intuitive meaning about the statistical independence in terms of the function shape of the joint distribution, right? Every slice and the squeezed version should be the same all the time. So that is the meaning. And then also from back to the mathematical definition of statistical independence, we start with this joint density, joint probability function, and then this one will always be written as this guy. So this is always true, right? But in this case, if this is further the same as this guy, okay? Oh, sorry. Yeah, so let's say it is, sorry, yes, this, yeah, I did wrong 2 times. So it should be f of y, which means, come on. Okay, so it's a marginal density of just y instead of the conditional density, depending on the x values. So, so that is the exact definition of statistical independence. And so in this case, we can apply, just to prove this, we can apply this one. So this is our function g of x comma y. And then it should be weighted by the joint density, right? But in this case, this joint density can be written as this. So it is always true whether they are statistically independent or not. But if they are independent, and then this guy will become, or that can be replaced by this, right? So x, y, so it should be double integral, then x and f of y, g dx dy, okay? So in this case, we can kind of change the order between the integrals. And then we can easily prove that this guy is this times y times fy dy. Okay, so in this case, this is an fex and ey.
저 이 xy가 그 x, y
다시 한번.
그러니까 저기에서 이 xy가
네.
저 fx, y의 평균을
그러니까 f의 x, y는 가중치이죠. 그러니까 조인트 프로비비리티죠. 가중치 밸류여서 가중치 밸류에 대한 평균은 당연하겠지만 뭐 1보다 작겠죠. 그러니까 이거는 예를 들면 뭐 이런 거예요. 그러니까 뭐
저걸 확률을 가지고 있는 어떤
랜덤 베리어블인데 랜덤 베리어블이 뭐냐면 우리가 남자의 키, 여자의 키 이걸 생각했었잖아요. 그러니까 어떤 펑션이 있어요. 그러니까 펑션이 있고 이 펑션이 무슨 펑션이냐? 이 두 개의 곱을 나타내는 펑션이에요. 그게 뭐 그러니까 남매의 키의 곱, 이 과연 우리한테 무슨 의미를 가지는지 모르겠지만 하여튼 그 펑션을 생각해 볼 때, 즉 x, y로 이루어진 펑션이 두 개의 곱으로 정의가 될 때 그 곱의 평균값은 그 곱의 평균값은 따르따르 평균값을 곱한 것과 똑같다. 그래서 그러니까 이 경우에는 이게 어떻게 되느냐 하면 자 이거를 그냥 x라 그러고요. 이거를 y라 그러고죠. 그 다음에 이게 페어로 존재하고요. 그죠? 우리의 이벤트 아웃컴, 그러니까 하나하나 인스턴스들은 이렇게 페어로 존재해야 되고 이거 하나하나에 해당하는 가중치 값이 이거예요. 즉 그래서 이거는 이게 아니라 f of x, y여야 되죠. 그러면 자 여기서 x의 평균은 어떻게 되죠? y와 상관없이 이 값 곱하기 이거 곱하기 이거 곱하기 이거가 돼요. 그죠? 그래서 평균 낸 거고 y에 대한 평균을 따로 내면 요렇게 한 거죠. 그죠? 그렇게 냈을 때 평균값이 각각 따로 나오겠죠. 그래서 그게 163, 172 이 정도 나왔다고 치면 이거 두 개를 그냥 곱한 값은 이제는 평균을 다른 방법으로 내는 거예요. 요 두 개 값을 일단 먼저 곱하고 요 확률을 해요. 그 다음에 그 곱한 값들의 평균을 계산을 하면 이 두 개를 평균을 처음에 한 다음에 그걸 하는 것과 똑같다는 거죠. So in this case, the example of E of x times y, which is the product between these two values, and then the associated weight values will still be these guys. So we can perform or compute the weighted average in that way. But that result of this E of an x times y will be the same as the product. So we first compute the average or weighted average only using x and only using y, and then we have two products, and then we just multiply them later. And that result will be the same as this guy. When? If x and y are statistically independent. Okay, so in this case, two independent random variables and then the covariance becomes 0. So again, statistical independence is much more strict condition than zero covariance or uncorrelatedness. Okay, so if they are statistically independent, and then the correlation will be 0 or covariance will be 0. But even if they are uncorrelated or their covariance is 0, but still they may not be statistically independent. So this corollary is about that. And then this guy, we talk about this variance, but now this transformed version of random variable x, y. So we consider the function of g of x, y, where we take the input of x, y, and then it will give some value. Okay. And then for this value, we consider now its variance. So that's the meaning of the left-hand side. And then that value can be computed in this form. So let's see how many slides we have. So yeah, I'm not gonna give a full proof for it, but you first have to consider. So in order to compute the variance, we first need mean or average value, right? So again, computing the variance requires the average or the mean. So we first have to compute the mean value of this random variable. That is exactly the same as this guy, x plus b e y plus c. And then if you guys remember, for any general function g of an x, y, where we have a joint density, its variance can be represented as this guy. So g of x, y. So this is our function value, right? And then the mean of g of an x, y. And then we just take the square of it, and then we just multiply its associated weight value, which is our joint probability value, right? So this is how we compute this the variance of the general function of g of an x, y. So in that case, we just plug these values into this g x, y, and then what is this value? So this value is this guy, right? If we plug those values into these corresponding position, and then we can compute, we can derive this guy. So this was a kind of general form. So in terms of the meaning, so we stretch the random variable x by the amount of an a. So if we have two height, 170 and 185, as boys and girls height, and then we just multiply the boys height by 3, and we multiply, for example, the girls height by -2, and then we just add maybe 100. Okay, so in that case, 3 times x minus 2 times y plus 100. Okay, so which follows exactly the same form of this. So in that case, so we kind of understood this is the derivation, but in the case of a simpler form, where we only involve x value without any y, in that case, so c is like the shifting, so parallel movement. So in that case, it doesn't influence our variance. So I think you are familiar with that. And then this x value is stretched by the factor of an a, and so this a squared will be the new stretching factor of your variance. Okay. And then here in this case, just the shifting or the translation. So it's called the parallel shifting is actually called translation. If you took the previous class of linear algebra in the previous semester, and then you already have learned it. And so the translation is the mathematical term representing the parallel shifting. Okay, in that case, it doesn't influence the variance. Then in this case, it doesn't matter if we have plus c or not. The variance is still the same as this guy. And then here, between those two, so we just simply represented the variance of an x as just sigma squared, I mean. And in this case, so where we don't have c value in this specific case, and then this can be represented as this, but this is not always true. So it's only works on, or it's only true when they are statistically independent. Okay, so back to this guy. Let me clear this page. Back to this guy. So as you guys know, plus c or not, it doesn't influence at all about our variance. So we can just simply remove them or ignore them. But in this case, so here in this case, we do not see any terms containing c, right? So that makes sense because it's not dependent on the c. So this is the general form. But if x and y are statistically independent, then they are uncorrelated, which means the covariance or correlation coefficient becomes 0, which means this part will be taken out, or they will be 0. So that way, if x and y are statistically independent, and then this equation will be true. Okay, so for minus sign, it will be remaining as just plus because all are taken squared. Okay, so we consider the squared values. So you can easily prove it, I believe. Then in the case of multiple ones, multiple random variables that we have, and then they are all independent, and then the variance can be represented as this guy. Okay, so so probably So yeah, let's think about this measure. No, sorry. So let's think about the variance of an x and y. Okay, so so yeah, we talk about the boys and girls height. So we still use this example, and then regardless of the girls' height, we can compute the variance for boys' height. And also we can compute the girls' height, regardless the variance for the girls' height, regardless of the x value. Right? So that's the variance for x only and y only. Right? So in this case, so so this is the general form. So let me get back to this guy. Okay, let me clear it again. So let's fix a and b as 1, and then this guy will be removed, and so this part will be just the variance of x, right? Although our event outcome is always a pair of boys and girls height, but we can just ignore the girls height, and then we only collect all the boys height and then compute the variance as just usual. So that's how we compute this sigma squared of an x. And then we can similarly compute the sigma squared of an y. Okay? And in that case, the joint random variable, the new function of an x plus y, which means the girls and boys and girls height, and then we consider their summation. Okay? And then those summation, this version of the random variable has the variance, which is actually larger than the summation of the variances of the original two random variables. So again, the boys' variance was 10, and then the girls' height variable was, for example, 8. But if we add them together and then we consider that function of x and y, and then the variance of that function is actually greater than 18. And why? Yeah, so I missed the one assumption that, so we still see this term, right? So the variance of an x comma y is actually composed of the three parts, where the first two part is the original variance of x and y separately, and then those covariance will be added together. So in this case, if x variance was 10 and the variance of y was 8, and then the covariance, so this is sigma squared upon y, and sigma squared of x comma y, and that value, suppose that value was 5, and then we will get the additional variance or the larger variance by the amount of 5 when compared to just the separate two variables. So in that case, so we can understand that understand it in this way. So if they are correlated, and then if they are positively correlated, and then their variance, when they are summing up, and then their correlation factor actually plays some important role. So they are increasing the variance. Okay, so because they are moving together, usually. So they are moving together towards the same sign, same positive values or same negative values. So that way they will stretch those variance of the summation of the two random variables a little larger. But what about the negative correlation, which is the covariance? The covariance can be negative value. So in the case of negative covariance value, and then that negative covariance value will actually decrease the original summation of the two variance values. So this is our kind of baseline, 18. So that's the simplest case. But if they are kind of negatively correlated, so we talked about the negatively correlated example of like the amount of money that we receive from our parents compared to my brother's amount of money that he received, right? So they are negatively correlated, and then for each variable has random variances, and then compared to the summation of the two random variable, the total the variance will be smaller, because if one gets larger and then the other gets smaller, so the difference from the mean to that value will be diminished or decreased. So that's kind of a intuitive understanding about this equation. So although I could finish this chapter, but we will have to continue the Chebyshev inequality next time. Okay. So have a good rest of the week, and then let's meet next Monday. 네, 안 끝났어요.
이거 할 때 X, Y 곱이라는 게 약간 아까 남매 키 얘기하셨잖아요. 그러면은 극단적으로 비유를 하면은 1이랑 180인 경우가 있고 X 변수가 2랑 90인 경우가 있잖아요. 그럼 그 곱은 같잖아요.
네.
그러니까 이 X, Y는 단순히 진짜 그냥 실제로 X, Y 숫자의 곱을 얘기해요. 그러니까 X는 180이고 네. Y는 2일 확률이랑 그러니까 182랑 92랑 그러니까 다 다른 경우로 계산하지 않는다는.
네네 맞아요. 그래서 그것도 좋은 지적이고요. 여기서 이거 두 개에 대한 어떤 펑션이 있잖아요. 이 두 개에 대한 어떤 펑션이 있어서 그거를 이제 g of x, y라고 했을 때 이게 두 개의 값은 각각 달랐지만 뭐 예를 들어서 합은 예를 들어서 한 330으로 항상 동일했어요. 그러면은 계산은 똑같아요. 이 330에다가 요거에다가 요 값을 곱하는 거예요. 근데 그 말은 요 값이 똑같아졌다면 이거를 어떤 새로운 랜덤 베리어블로 본다면 이거의 이벤트 스페이스, 그러니까 유니크한 중복을 허용하지 않는 그런 형태로 본다면 330이 한 번만 존재하고요. 이 새로운 랜덤 베리어블에 대한 확률 값은 요 두 개 케이스에 대한 확률 값을 더한 게 되겠죠.
그러면은 그러니까 그냥 임의로 변수 4개 있다고 하면은
네.
그러니까 이거에 그러니까 그럼 그러니까 두 개씩 있으면은 나올 수 있는 가지수가 4가지가 있잖아요.
네.
합이. 그러면은 그러니까 그 각각의 같은 안 같은 이거의 확률이 있고 밑에 거의 확률이 있잖아요. 그럼 이거의 곱이랑 그 확률의 결국 곱이잖아요. 그러니까 이거의 곱이 일어날 확률의 일부잖아요. 이게.
네.
그걸 결국 다 더하면 같다고.
네, 그러니까 같은 값으로 귀결이 됐다 그러면 그 각각의 다른 경우에 해당하는 확률들을 더해주면 돼요. 그리고 똑같은 값이 나오는 경우는 지금 얘기했듯이 뭐총 4, 그러니까 x와 y가 각각 2가지 서로 다른 값을 가지면 x, y는 뭐 4가지 값이 가지지만 x 곱하기 y를 계산했을 때는 그게 유니크한 밸류로는 뭐 한 2가지 값밖에 안 나올 수가 있어요. 지금 중복이 되면.
그러니까 결국은 그러니까 변수가 같아도 확률이 여러 가지 그러니까
변수가 가지는 값이 같아도
네, 그러니까 그때 주사위 예시를 들어주셨을 때도 1, 2, 3, 3, 5, 6 그렇게 나오셨잖아요. 그 3, 3 각각
그렇죠.
6분의 1 확률이 있는데
그렇죠.
결국은 같은 거니까 그렇게 본다고.
맞아요. 그렇게 이해하면 돼요. 네. 네? 그래요? 아니 나 이거 나 고등학교 때 배운 거라. 안 그래요?
네, 이것도 영어로 보니까 영어로 또 보고 어려운 거 특정은 잘 알아요.
그래요? 아니 사실 뒤에 쪽이 좀 안 새로운 고등학교 때 배우지 않은 부분들이 좀 그쪽에 좀 더 집중을 하기 위해서 이쪽은 좀 내가 조금 빨리 나가는 경향이 있거든요.
안 그래도 영어도 살짝 하고.
네. 네. 아니 뭐 고려해볼게요. 네. 네.
이거 저번에 물어봤었는데
네.
이거 두 개는 일단 인디펜던트 하지 않잖아요.
네.
코릴레이트 할 수 있어요?
그러니까 이 경우는 평균만 동일하게 유지되면
네.
여전히 언코릴레이티드일 거예요. 그러니까
네.
코베리언스를 계산하면 0이 나와요.
네.
그런데
코릴레이트를
네.
이거를 그래프로 표현하면 어떻게 돼요? 정규
코릴레이티드를 그러니까 그러니까 코베리언스라는 개념이 있고요.
네.
그 다음에 코릴레이션이라는 개념이 있어요.
네.
CORR이라고 쓰면 코릴레이션이라는 개념은 코베리언스에 그냥 단지 그냥 값만 노멀라이즈를 해준 거예요.
네.
그러니까 이 값은 뭐 예를 들면 한 마이너스 30, 뭐 플러스 80, 뭐 이런 여러 가지 값을 가질 수가 있어요.
네.
저기 가장 작은 값이나 큰 값이 뭔지 몰라요.
네.
단지 근데 그거를 항상 어떤 랜덤 베리어블이건 상관없이 이거를 어떤 수로 나누면
네.
그게 항상 마이너스 1에서 1 사이의 범위로 항상 들어오게 되는 형태로 나눠준 버전이 코릴레이션이에요.
아 그러면 이런 정규분포만 봐서는 판단할 수 있겠네요.
그 내가 이야기하려고 한 건요. 이거 두 개는 그냥 뭐 서로 다른 개념이 아니다라는
네,
이야기를
네.
한 거고요. 결국 그러면 코베리언스가 0이 되면 코릴레이션도 0이 되고 이게 0이 안 되면 이것도 0이 안 되고요.
네.
그러면 코베리언스만 생각을 해보면 코베리언스가 0이 안 됐을 경우는 뭐냐 하면 x 값에 따라서 y 값의 디스트리뷰션,
네,
그
네.
컨디셔널 디스트리뷰션이 그러니까 x가 정해졌을 때의 y 디스트리뷰션은 컨디셔널 디스트리뷰션이 x 특정 하나에 대한
네.
그 디스트리뷰션의 평균값이 이렇게 막 변하는 거예요.
네.
x가 남자키가
왔다 갔다 일정하지 않고 왔다 갔다 하면은
평균값이 중요한 거예요.
네.
평균값. 그때 얘기했던 뭐 가평균 얘기하고 그랬었잖아요.
네.
그러니까 트루 평균을 집어넣었을 때 여전히 0이 나온다. 즉 그 말은 가평균이나 진평균이 똑같다. 뭐 이런 얘기잖아요.
네.
그러니까 그 말은 이 어떤 모양, 디스트리뷰션의 모양으로 보면 이게 원래 평균, 그러니까 여자가 가지는 원래 평균값이 있어요. 남자 키에 구애받지 않고 그 값이 165다. 그랬는데 남자 키가 175였을 때는 여자 키의 디스트리뷰션 혹은 그 특정의 경우에 해당하는 여자 키의 디스트리뷰션의 평균값은 얘가 가지는 오리지널 평균값보다 달라진 거예요.
네.
그 달라졌을 때는 그 코베리언스가 0이 안 나오게 돼요.
네. 어떤 건지 알겠습니다.
네.
알겠습니다.
How about okay.
Because we graduated in 2014,
Okay.
we didn't study this, so we have like part-time. And I'm trying my best to memorize it. Even I studied self-study, but I not fully understand. Even though your teaching is very good, even in examples.
I totally understand.
Yeah, but we have like chai,
Yeah, that's right. Yeah. So
I'm trying my Korean.
yeah, totally understand.
But you know that all the Koreans that study this in high school,
Yes.
they are good. They are better than us.
So yeah, I mean, yeah, my best advice would be to just carefully follow the book. So although I skipped most of the examples contained in the book, but every pieces that we learn, for example, like this, and then right after this, the book will give the example to help you understand about what this means. Okay, so I understand it takes some time for you because you are kind of less familiar than other students. Compared to other students.
So this is the first year course. And then we start with this course.
So yeah, let me see if we can have additional kind of review session for the previous ones. Yeah, I'll definitely
That
consider it.
will be like helpful for us.
Yeah. And then if you can, please spend as much as your time.
I'm spending
just
much.
yeah.
You are spending
Okay,
much.
Then just just to read the book as much as possible, and then. If you have any questions while reading the book or studying the book, just feel free to ask me any questions. Outside of this class, so I'll be available. Generally outside of this class, so we can be separated to discuss about your questions.
How can I contact you?
Oh, so you can send me the email. Okay, that's good. Okay. Great, yeah. Keep up the good work, please. 네.
영어 한국어 하니까 그래서 So are you gonna check attendance? 출석은 안 할 거예요?
해요. But I didn't have a chance to check at all so far. But,
저번에
네.
애플이라서
그거를 그래서 오늘
다음 주
하려고
시간이
했는데
있구나.
하려고 했는데 내가 까먹고 못했어요. 그리고
아.
어떤 학생들이 저기 좀 먼 데서 온다고 출석 시간을 한 5분에서 10분 정도 좀 늦게 해달라고 이야기를 한 친구가 있어요. 그렇게 하려고 하는데 처음 수업을 스타트 해갖고 이렇게 좀 이렇게 계속 하다 보니까 내가 나중에 잊었어요.
그러면
하긴 할 거예요 언젠가. 네.